So this is a solution, a graphical solution of the linear program minimize 6x plus 4y subject to 2x plus y greater than or equal to 12, x plus y greater than or equal to 10, y less than or equal to 4, and the non-negativity constraints x greater than or equal to 0 and y greater than or equal to 0. So the first constraint, we're going to sketch the feasible region. The first constraint is 2x plus y greater than or equal to 12. It passes through the points 0, 12 and 6, 0. Those 2 points can be obtained by alternately setting x equal to 0 and y equal to 0. Also x plus y greater than or equal to 10. That goes through the points 0, 10, 10, 0. Again, obtained by setting either x equal to 0 or y equal to 0. The third constraint is parallel to the x-axis, y less than or equal to 4. So if it's incorrectly specified as 14, so it should be 4. And to show it there. So you can see that we're shading the north side of the first two constraints. We know to do that because we just pick a point and see if it satisfies the equations. If for example, you could pick point 14, 0, and then test that point in either of the two constraints, and you'll see that it is satisfying both. So we want points on the north side of both of these constraints. For the third constraint, it must be less than or equal to 4. So right now, the feasible region is this darker shaded blue here. Once I've added the non-negativity constraints, the feasible region is going to be bounded. Actually, it's unbounded, but you can see it's contained by this y is equal to 4, or y less than or equal to 4 constraint. The second constraint here on the left, and then from below by y greater than or equal to 0. To solve this, we're going to add the gradient of the objective function and just set it equal to some arbitrary number. I'll just, for example, set it equal to 100 initially. I'm going to shade this in red and make it dotted to emphasize that it's the gradient function, the objective of the gradient function. So the gradient of the objective function. Style a little thicker and make it dotted and red. Okay, now the idea is to progressively minimize this value that it's set from 100, because we set it equal to 100, and it's going to be set progressively lower, and this is going to move in this direction to the point where it's finally going to leave the feasible region, and I think it's going to leave at this point here, which is the point 6, 4. So I'm going to just create another couple here, 6x plus 4y equal to, let's say, 70. You can see it's getting progressively smaller in value. Now it's unequal to 70. Essentially what it's doing here is it's dividing through by 2, so that original 100 became 50, but the coefficients became 3x and 2y instead of 6x and 4y. But this process of minimizing essentially is by reducing the value of the objective function. Okay. Now I know that it actually is optimal at this point here, 6, 4, and it has a value of 52 at that point, so I'm just going to punch that in. That didn't quite work out. 6x, and there we have it. So that's the objective function gradient at the optimal solution, which is 6, 2. And I think I'm going to beef it up quite a bit just so that it emphasizes that it's at the optimal solution right there. Okay. And so we have the optimal solution, 6, 4. The value of the objective function at that point is 52. And that's the solution.